So we're finishing up 6.3, talking about identities and proof. And this is really kind of the core of a lot of what we'll wind up doing in trig and how it kind of carries on throughout when we start to integrate it with calculus a little bit and kind of moving forward. So the first thing we want to do is expand our library of functions with three more. And those are our reciprocal functions, and there are three, right? So you have cosecant, um, which we abbreviate typically as CSC theta, although IB likes to abandon the three-letter abbreviation for some reason and do this. I don't know if this is an international thing or just an IB thing, but if you see that in the book, that's what it means. And cosecant we define as the reciprocal of sine. Next we have secant, and that's the reciprocal of cosine. And tangent, we have, I should say cotangent. Cotangent is the reciprocal of tangent. So you have cosecant, secant, and cotangent. The one thing I want to mention here is that normally we're used to kind of seeing this x to the negative 1 notation to mean the reciprocal. This does not apply here. So to say like sine inverse theta is its own function, as we've learned, right? We know that this is the inverse sine or arc sine. It does not mean cosecant, right? So just be careful with that notation. But for example, if I wanted to evaluate one of these reciprocal functions at a particular angle, I can do that by writing it in terms of another function, right? Cosecant is 1 over sine. We know that 1 over sine 30, we know that sine 30 degrees is 1/2, and 1 over 1/2 is 2. Right, so we can kind of expand our library of functions. For example, given that theta is a reflex angle and that cosine of theta is 3/5, find the values of the remaining trig functions. Well, we're going to attack this very much the way that we would attack this earlier, right? So we know that if theta is reflex, and and cosine is very clearly positive, well, this puts us in quadrant 4, which will be helpful later. So I like to sketch it out just to just to have it as a reference. So my angle is going to be out here somewhere. I would drop a perpendicular. This is theta, but as we know, we can do everything based on our reference angle. And so I'm going to draw my triangle so that it's oriented the way that it is in the coordinate plane, right? And we're kind of working off of here. If cosine theta is 3/5, then adjacent side is 3, hypotenuse side is 5, and this is a right triangle. Whether we called this, say, like 3 and 5 or 3/5 and 1 is not important right now. Proportionally, it all still works out. Well, that, of course, tells us that our opposite side is 4, and we can start to find our remaining trig functions. Right, so we need to know sine, cosine, tangent, and then we now have our expanded reciprocal functions, cosecant, secant, I do that every time, and cotangent. So now that I've got my triangle figured out, right, sine is negative 4/5 because only cosine is positive and it's reciprocal. Cosine we're told is 3/5, tangent is negative 4/3. Cosecant, secant, and cotangent are just the reciprocals, right? So you have negative 5/4, positive 5/3, and negative 3/4. So just kind of an introduction to those first few functions. Let's get into some talk about identities now. And I want to start with kind of the most basic two, kind of our building blocks, so to speak. If I just consider any angle, actually maybe I'll pick a different color here. If I consider any angle, and we'll pick one that's acute just to keep it simple for now. If I would consider just any kind of angle here and its trig function, right? Sine of theta would be kind of the opposite side over the hypotenuse, right? And the hypotenuse is always 1 in the unit circle. And so it just kind of holds up that sine of theta is exactly the opposite side length. So we're just going to call this sine of theta for now. And the same logic is true with cosine, right? If this is adjacent, actually let me move this because I'm going to need that space for later. If cosine is adjacent over hypotenuse, and my hypotenuse in the unit circle is 1, well then cosine theta is exactly equal to the adjacent side. So let me label that. Well, then it holds up that if I were to calculate tangent, then tangent is opposite over adjacent. It's just sine over cosine. And this is the way that we would derive the tangent function, is as the quotient of sine to cosine. Of course, then we can consider cotangent as its reciprocal as cosine over sine. The other thing that we should notice maybe immediately, hopefully, is in a right triangle, the Pythagorean theorem will hold up. So based entirely on my Pythagorean theorem, from the Pythagorean theorem, it's true that sine squared plus cosine squared is 1. So these two are the most kind of fundamental for us. But we can play with these some more. Maybe I want to put this Pythagorean identity in terms of tangent instead. Well, I can manipulate these, right? If I decide to find a way to express this in terms of tangent, well, if I were to divide everything through by cosine squared, sine over cosine, as we just learned, is tangent. So this is tangent squared plus 1. And then 1 over cosine is secant, so this would become secant squared. So here's another kind of variant of our Pythagorean identity. The same can be true if I try to eliminate sine in some way, right? I can divide everything by sine. So you get 1 plus, we just learned that cosine over sine is cotangent, so this is cotangent squared. And then 1 over sine is cosecant, so this would be cosecant squared theta. Move this over a little bit. So we have our main Pythagorean identity here, this is kind of the big one, and our two variants that sometimes also come in handy here and here. Here are kind of our big two and kind of their associated identities. So if we want to look at an example that uses these, if we're given that theta is an acute angle and we're given the value of sine, we want to find all of the other trig function values. Now we could go through and draw out the triangle and find the hypotenuse and all of that, but we can speed up the process by just applying our identities. So if sine, cosine, tangent, cosecant, secant, and cotangent. Theta acute immediately tells me I'm in quadrant 1, which tells me that everything is positive. All right, so let's get to work. I know sine, I can find cosine because the two are linked through the Pythagorean identity. So sine squared is going to be 2 over 9 plus cosine squared equals 1. And so cosine squared is 7 over 9. And then, cosine theta would be root 7 over 3. So we know sine, it was given to us, and cosine root 7 over 3. Did I do that right? Yeah. Tangent, we know, is just sine over cosine. Right, so I have root 2 over 3, and then root 7 over 3, which is going to simplify to root 2 over root 7. And if I wanted to rationalize this, I could, right? I could just multiply everything by root 7. So I come up, that's the wrong color, come up with root 14 over 7. And I have my sine, cosine, and tangent. Everything else is just a reciprocal, so I have 3 over root 2, which is going to rationalize to 3 root 2 over 2. Secant, which is going to kind of work the same way, 3 root 7 over 7. And cotangent, 7 over root 14, which is going to simplify. 7 root 14 over 14, okay, which is going to reduce to root 14 over 2. Much faster than drawing the triangle, trying to calculate the hypotenuse, put it all together one at a time. Everything is right there, right? We used my Pythagorean identity, we used the quotient identity, and then we used my reciprocals. 1, 2, 3, done. Let's look at a couple others. So the sum and difference formulas, there's a proof in the book. I'm not going to go through it because it's pretty dense, geometric in nature. Look at it if you're curious, but these are kind of the two big ones. I'm just going to go through maybe some big things that you might notice or pick up from the formulas that are presented. So you have sine A plus or minus B, right? Doesn't matter if we're considering a sum or a difference, this formula holds up either way. So I have sine A cosine B plus or minus cosine A sine B. What do you notice? Well, let's pick this apart. The first thing you might notice, if I pick a highlighter here, is that the plus and minus stays. So it's always going to stay the same. And you might notice too that the trig functions that are paired up as products, I'll do it this way, are different. So I've always have it set up with this AB, AB. But sine and cosine are paired together, and then we flip them, cosine and sine. So there's your sine sum and difference. Your cosine sum and difference, maybe you noticed already just glancing through it, that my plus and minus is flipped between writing it in kind of its condensed form and writing it in its expanded form. And you might also notice that the functions are paired together, right? So the cosines are all together and the sines are all together. They have to come in this order because of that subtraction that kind of comes into play. The way I kind of like to remember part of the order is to say that whatever function comes, where's my highlighter again? Right, whatever function comes here is the function that comes here. Whatever function that comes here also starts the formula. The proof for tangent isn't terrible. It's just not necessarily clean, but let's go through it anyway. Let's see how this kind of came about. I know from my quotient identities that tangent is sine over cosine, so I can start there. Based on what I've just learned, I can expand that, right? I can call this, actually I'm going to move this down because I need some room. Right, this would be sine A cosine B plus or minus cosine A sine B. And then cosine is going to be cosine A cosine B minus or plus, it flips, sine A sine B. And we feel like we're kind of stuck here. So the way we're going to kind of hack this proof is to multiply each part of the fraction, or really divide it, I suppose, by cosine A cosine B, or the other way to look at this would be to multiply it by 1 over cosine A cosine B. And you might be wondering why. It feels kind of arbitrary. Yeah, well, it is. But it does help us. So if I write this all expanded like, I have sine A cosine B over cosine A cosine B plus or minus. You can see why this is a little bit tedious. I will have a link to make sure if you don't want to see the proof, you can skip over it. I would never test you on a proof that has kind of that arbitrary step. But I do know that a lot of people, including myself, find it easier to learn these identities when you know how I got them, how we got them in the first place, which is why I like to walk through some of these proofs when I have the time. So a lot of stuff cancels out. Cosines, cosines, well, this whole term, and then nothing in our last term in the denominator. However, Sine over cosine is tangent, so this is tangent A. Sine over cosine is tangent, this is tangent B. Everything cancels out, 1. Sine over cosine is tangent, tangent A, tangent B. So here is my sum and difference formula for tangent. The way I like to remember parts of this is to look at it and say, well, originally sine was in the numerator, and when I expand sine, it has plus or minus. Cosine was in the denominator, and when I expand cosine, it's minus or plus. So I kind of use that trick to keep my pluses and minuses and pluses straight. Well, let's put this into action. If I want to evaluate sine 105, I don't immediately know this, but I know some tools that can help me out. Right? I can rewrite sine 105 as 45 plus 60. Right? And these I have values for. We learned way back at the beginning of 6.3 how to turn these into kind of my special angles, right? We have 45, 45, 90 case triangles and 30, 60, 90 case triangles. I know these values, so I can now expand sine, cosine, cosine, sine. And evaluate what I know, right? Sine 45 is root 2 over 2. Cosine 60 is 1/2. Cosine 45 is root 2 over 2, and sine 60 is root 3 over 2. Combine this all together, and we get root 2 over 4 plus or minus root 6 over 4, and this is just going to stay root 2 plus or minus root 6 over 4. Remember that I cannot add or subtract underneath, oh sorry, this should just be plus. All this should just be plus. Remember that I can't combine underneath a radical under addition. So that stays this way. It does not become root 8 over 4. It stays just like that. So starting to apply these formulas. We're going to apply them one more time to prove another class of identities called double angle identities. And the proofs for these come right from what we just learned with the sum and difference. So sine of 2 theta. Well, how can I write this using something I've already learned? I can write this as sine. Actually, I'm going to use a different color so kind of the proof is separate. I can write this as sine of theta plus theta. And I can use my sum and difference. Sorry, this would just be a plus. I can use my sum and difference formula. And if you've noticed, these are, I'm going to use something a little more muted to fit in, I suppose. Notice these are the same. Right, multiplication is commutative, so these are effectively the same. So I have 2 sine cosine terms. And that right there is my identity. Sine of 2 theta is 2 sine theta cosine theta. Same logic applies for cosine, but there's a couple extra kind of play with it steps that we have to play with, right? Let's stick with my color scheme first of all. Let's stick with the same logic, theta plus theta. Cosine, cosine, sine, sine. Condense a little bit. This is cosine squared theta minus sine squared theta. This is the first one of my cosine double angle formulas. And you're saying, what do you mean first one? I can rewrite this because sometimes it's not helpful to turn one trig function into 2, right? I want to be able to write this in terms of one trig function always. Well, fortunately, I've learned another identity that will allow me to make substitutions for these sine squared and cosine squared terms, right? With my Pythagorean identity right here. So the first thing I can do is maybe substitute out for cosine. All right, so this would allow me to say 1 minus sine squared theta minus sine squared theta, which I can reduce to 1 minus 2 sine squared theta. So here's another one of my identities. And then the other thing I could do is follow the same logic and substitute out sine. So if I kind of go back to this, let me draw a couple arrows here, I suppose. This would be to say cosine squared theta minus 1 minus cosine squared. So this then becomes 2 cosine squared theta minus 1. And there's my third identity. This would be an equal sign. So we have 3 ways of writing cosine 2 theta. 3 useful ways, right? I have this difference of squares that may be useful at some point. But functionally, most of the times, these are the 2 that are crucial, right? 1 minus 2 sine squared and 2 cosine squared minus 1. So here are my formulas for cosine 2 theta. Last but not least, we have tangent. And we're going to follow the exact same logic, right? Color scheme. There we go. Tangent theta plus theta. So apply our formula. Tan theta plus tan theta over 1 minus tan theta tan theta. Simplify this. I get 2 tan theta over 1 minus tan theta squared. So my identity for tangent is right there at the bottom. 2 tangent theta over 1 minus tangent squared theta. Again, I like to go through all of these derivations of identities like we've done, really to start identifying where these come from. You'll have these on your formula sheet, but a lot of times it helps to understand why. And if you ever get to a point where you don't have your formula sheet, or maybe you just don't have the time to riffle through the book for the exam, you know how to come up with these formulas. So that way, if it's easier for you to just kind of do out the derivation really quick, you understand how you do it, where it comes from. So let's put these into action. Use a double angle identity to prove that cosine 60 equals 1/2. So my question then is, can I write cosine 60, or can I write 60 really, as 2 times something? Yes, I can, right? 2 times 30. So I can use any of my double angle identities. We'll just use the first one because it gets neglected pretty often. So let's show it some love. Cosine squared 30 degrees minus sine squared 30 degrees. We know that cosine of 30 is root 3 over 2. That's going to get squared. We know that sine of 30 is 1/2. That's going to get squared. So I have 3/4 minus 1/4, which is 2/4, which is 1/2. End of proof. Speaking of proofs, let's talk about proving some of these trigonometric identities, just like we have been. But a lot of great tips here. So one leg up that you have compared to when I've taught this in pre-calc is that you have already covered a lot of proof. Right? This is just a form of direct proof like we talked about in chapter 1. Right? My goal is to get the left-hand side and right-hand side equal to each other. Some extra tricks that we can use in trig, because it's very easy for this to turn into a circular argument and kind of go down a rabbit hole for hours and not get anywhere. So some tricks that you can use. Kind of as before, right? Look for opportunities to factor. Or to add fractions. So a classic thing people like to do with these problems is to provide some sort of fraction to deal with. First step, if you see 2 rational expressions, is add them together. Obviously, if you're going to prove trigonometric identities, you're probably going to use some of the fundamental ones. Use the identities we have already proven. And this is really the biggest one. When in doubt, write everything in terms of sine and cosine. Everything at this point that we've learned can be written some way into sine and cosine. So if you're ever stuck, just reduce everything to that and work from there. For example, if I want to prove that tangent theta plus cotangent theta is equal to secant theta cosecant theta, it's not really immediate where to go, right? It's not really obvious right away where to go with this, so let's just turn our whole left-hand side into sines and cosines. So tangent, we know, is sine theta over cosine theta, and cotangent is tangent's reciprocal, so that's got to be cosine over sine. Rule number one, add fractions. My common denominator is going to be cosine sine. So I have sine squared plus cosine squared in the numerator, which should hopefully tip you off because that's a Pythagorean identity, and sine squared plus cosine squared is 1. And then I have my reciprocals. So this 1 over cosine is secant, 1 over sine is cosecant. That's my right-hand side. End of proof. These are just the same proof techniques that we've talked about before, just with a little bit of a new flavor, so to speak.